Okay, everyone, welcome to HoTT. It's 11:30 on November 5th, 2020. And as America is choosing between a conservative and a moderate conservative with a lot at stake, we're expecting big news coming soon from Nevada and Arizona. And to deliver this big news is Nima Rasekh, because the big news for us is elementary models of homotopy type theory and, of course, filtered products. So, Nima, the stage and the moment are all yours.
Okay, thanks, Chris, for, inviting me. And I have to say right away, I have no big news about anything Arizona related. I'm sorry if you were hoping for that. Okay, so moving on to type theory. So as the title says, the goal of the talk is to talk about filter products and elementary models of homotopy type theory. And as the people who might already know me might be aware of, I'm really a homotopy theorist by heart. I'm not really a type theorist, but I like to give talks on type theory seminars because the homotopy theory I like is kind of connected to type theory, as you will see in this talk. So I'm not a native, but I'm always glad to visit. So let me start by using one of my previous slides that I've used before, exactly as I've used, because it's a nice intro into what I want to talk about. So the way I see this, all of math is just divided into how to write things down and what they mean, i.e. the syntax versus semantics, or type theory versus category theory. And on the extensional and one categorical side, there's already like tons of cool results of what the relation is, how to construct categories, so-called elementary toposes out of extensional type theories, and how to like model these type theories inside them and so on. But for the infinity story, there's a lot of stuff we don't know yet, right? And this is also another one of my slides that I've used before. So up to here, I could just copy paste my previous slides. So it's easier to make them. And as you notice, so there's like this kind of the left column with all various type theories with different constructors. And the right column was kind of various infinity categories. And the dream someday is to have like this perfect correspondence where when I start on one side, I can just easily go to the other and vice versa. But we are far, far away from this dream. So this is like, it's really a dream for now. And the goal of this talk is to focus on this last line, right? For now, I want to start by focusing on this last line. And in particular, what do I mean with this? If Grothendieck, then I get homotopy type theories. So what is that supposed to mean? And maybe a good starting spot is to even say, what's a model for HoTT? Like, what should it even be? What's that supposed to mean? And here's a vague edition, so not precise. Vaguely speaking, it should be true that if I have a model for HoTT, it should be some kind of infinity category. And I should know how to interpret these various type theoretic constructors inside that infinity category. And for some, it's reasonably obvious what that means, right? So if I have like something like a natural number type or a coproduct type, then I know, right? Like there's an easy, well-defined notion of coproduct. I can just talk about this coproduct, universal property, and so on, and it works well. But for some constructors, that is not true, right? So famously, the most famous example is univalent universes, right? So there's a nice strictness on the type theory side, whereas on the infinity side, it's all, everything is up to contractible ambiguity, everything is up to like certain homotopies, coherences, and so on, and that doesn't translate well on the type theory side. So it's a problem, right? Like the problem is, how do you make an arbitrary infinity category a strict object? And for some cases, we can do something cool. We can actually restrict. Concretely, so there's this, if you imagine all of infinity one categories being that black box, inside that black box, there's this nice blue box of model categories. And so model category is an actual strict one category with some extra data, fibrations, cofibrations, weak equivalences that can recover for us in infinity one category. But because model categories themselves are strict, we can actually do strict concrete math with them. And in general, they're not the same. So every model category gives us an infinity one category, but not every infinity one category comes from a model category. I mean, I guess just to convince you, the most obvious reason, every model category has finite limits and colimits, but not every infinity category has finite limits and colimits. They can just be something. But it turns out if you intersect those two, in one place they actually coincide, namely presentability. So if I do restrict my attention to presentable infinity one categories, then they correspond precisely to combinatorial model categories. So there's like this nice, that's where they actually do coincide. So at least for presentable model categories, we're good. We actually cover everything. We can just focus on model categories. And now we can try to understand what does it mean for a model category to model certain aspects of HoTT. And lots of people have thought about this. Lots of like really cool people have thought about this problem. And here's like a cool list of a bunch of results that exist in literature. So for example, Arendt and Kapulkin have defined this notion of a logical model category. And then they have proven that it already models certain types that occur in Homotopy type theory, like sigma types, pi types, and identity types. Then Shulman kind of generalized this and then has this notion of a type-theoretic model category, which also models pi types, but the pi types has a function extensionality, so even better. And then Shulman and Lumsden have this really cool paper, which have this notion of good model category and excellent model category, which are not very descriptive names, but they do have very cool properties. And so in particular, they model all kinds of stuff that you would expect from type theory. And then finally, Shulman has this new notion of a type-theoretic model topos, which is this recent paper that came out, I want to say summer of 2019. And that models all of the previous ones. So it satisfies all the three previous steps, but also has strict univariant universes, which nice. Okay, so after here, if you noticed, I used the word topos twice, once in slide 2 and now again. So why do I keep using the word topos? Where is it coming from? Why does it matter? So here's another kind of nice diagram. It's like the one benefit of slides is you can have these cool pictures everywhere. So here's a new diagram. And what does it say? It says, okay, topos is supposed to be in the one setting, i.e. in the extensional setting, where we don't have any identity types that fancy. They correspond to exactly the type theories. And if you restrict those exactly to the locally presentable ones, we recover what is known as a Grothendieck one topos. I mean, I guess usually people call it Grothendieck topos, but because we want to distinguish between the one case and the infinity case, I would try to add the one in the right places. So Grothendieck one topos is precisely the models of certain like higher order type theories that are also locally presentable. And so that's nice. That means they're models for type theories. That means to care about them. But the nice thing is they can also be defined in like a very kind of geometric way, right? So unlike elementary toposes, which are more connected to type theories, Grothendieck toposes can be just defined using some kind of sheaf notion, which is the next slide. So what is a Grothendieck topos? It's just a category G, and that fits into that adjunction like this. And so here, so in other words, I want an adjunction. I want the right adjoint to be fully faithful, right? So it's like the hook, and I want A to be left exact. And so notice here, if this fails, so this exactly, if this fails, then what can we say? Then that means G is exactly locally presentable, right? So that's how they correspond to each other. So locally presentable categories also come from pre-sheaves, and toposes are the ones which come from a localization functor that is also left exact, i.e. preserves finite limits. And so this can be readily generalized. It's clear how to generalize it. What's the correct homotopic analog of set? It's spaces. So all I do is I just replace my set with S set with the Kahn model structure. Kahn complexes are the correct kind of analog of space, like a model for spaces and the correct analog for sets. And then I take the diagrams and just give that a projective model structure. And now I want just some kind of model category, which is a localization of that, very analogous, such that the localization is again left exact. So that's a Grothendieck model topos, also called model topos, but because you want to distinguish with the elementary, I would also say Grothendieck. Okay, so this should be a model for homotopy type theory. That's what we would expect, right? Based on following our intuition from this slide, the fact that the Grothendieck one topos is a model for homotype type theory that is locally presentable. This should imply that this model topos should also be a model for homotype theory. And it should be exactly the locally presentable. So, and in the same way that presentable infinity one categories are completely recovered by the combinatorial model categories, there's a notion of a Grothendieck infinity one topos in its general infinity one categorical sense. And those are completely recovered by model toposes that we just defined. So I can completely focus on these. That's like nice. It's a very kind of strict category that can study with model categorical techniques. And my goal is to show that they are models of homotype theory. Okay, so How can we do that? And this is where Shulman comes in, defining what I just mentioned in the couple slides before, the type-theoretic model topos. So a type-theoretic model topos satisfy these like 4 conditions. So it's the underlying category is a Grothendieck 1 topos. Then it has like this model structure, which has enough axioms to do what we want. And then, okay, it's also Cartesian clause, which is reasonable. And it has this like weird 4th axiom, which I will talk about. So that's about universes. And notice I never said it's a Grothendieck model topos, but that follows. The axioms imply in particular it's a Grothendieck model topos. So that's one of the things that Shulman proves. And so what is this last condition, which is like weird, and if you're not familiar with the paper, it makes no sense. But it's really just saying that if I take the functor, so I take fib to be the functor that takes a point to some sort of small fibrations over x, right? So E here is the model category, right? So I can take that a class of fibrations over x, and then take the underlying groupoid, right? So notice this just means underlying groupoid. So this is, it's not actually a functor, it's a pseudo functor, right? Because the functoriality comes from pulling back fibrations. That's not strictly functorial, but it is pseudo functorial, so good enough. Then what he does is he defines this notion of a universe, which is a map, which is like an acyclic fibration over this fib functor. And then he proves that this condition, this mysterious 4th condition, implies the existence of such a universe. And then he also proves that this universe, if it exists, is automatically fibrant and univariate. So nice. This is kind of what we want. And this universe is kind of the kind of implementation of this strict univariate universe from type theory inside this category. It has all the kind of properties you want. Okay. So the question then remains that, do we recover all model toposes, right? So I said in the beginning, every model, a good type-theoretic model topos is a particular kind of model topos, but do we get all of them? Is this really true that all model topoi are a model for HoTT? And this is actually the second half of the paper by Shulman is proving that. And so what he does is he does the reasonable thing, and he kind of does 3 steps, right? So we already observed, so this is like a reminder, the first line is that we already observed that a model topos is just some kind of adjunction, localization of these presheaves. So he starts by observing, okay, the Kahneman structure is this, which is kind of already in the paper by Kapulkin and Lundstein, the simplification model. Then he moves on to the injective model structure, which, okay, now you might complain and say, wait, here there's a projective and here now there's injective, but they are equivalent, so it's not too bad. So up to equivalence, you can work with 2. And then he localizes and says, okay, still it's preserved if you do a left exact localization. So that's it. That proves then that I have a model for HoTT and I can recover all model topoi in there. And so this is kind of like a complete solution for the presentable case. Presentable exactly recovers all presentable infinity 1 categories, which are model for homotopy. Okay, so I guess this is a good point to stop and ask if there are any questions. Nope. Okay, then I will move on. So the next goal then is how about the non-presentable case? So I think it's not very controversial to say that we should have non-presentable models for homotopy typing. Because, I mean, why wouldn't we, I guess? But how can we prove that? How can we recover the non-presentable models? And immediately, if you recall the box, we cannot just use model categories. There will certainly be some infinity. I mean, actually, I don't know. There definitely are infinity categories which don't come from model categories, but I cannot say with confidence that the infinity categories, there are also models for HoTT that don't come from model categories. I would expect that maybe. So we don't know that.
I mean, the initial model will be, right?
But do we know it's not a model structure? It doesn't have a model structure?
Well, I mean, it won't be presentable.
No, I agree with that. I'm saying is there definitely a model? Is there like an infinity 1 category that is a model for homotype theory, but does not come from the model category? Like,
I think you would
exist a model structure such that the underlying infinity 1 category is equivalent.
So I don't see a very simple argument for that, but I think the answer is that we know that, yes.
Oh, I see. Cool. You should tell me about this.
But yeah, so I don't see a simple argument because, like, you can imagine that there would be some pathological model structure. So I think it would take a bit to unwind why it cannot exist. But
okay, cool.
I'm confident.
There you go.
Yeah.
So Chris says we definitely need non-model category cases. There you go. So what can we do?
Sorry, but did you say that the initial model shouldn't be presentable? That's what you said?
Yeah. Just because the initial model will be, I mean, this will be a model of types and terms. All the expressions in type theory are countable, right? There are only countably many expressions. You're not going to generate anything that won't be countable. So it's going to be very hard to have all small colimits. This is like a one sentence argument, but the model category argument is more subtle, I think.
Okay, I see.
Okay, that was a good discussion. Okay, so where was I? Aha, so what can we do? How can we tackle this question? And so here there are some possible options would be, so one very general argument is that one possible case, for example, is to say I can take every category and I can embed it in this presheaf category. And then that presheaf category is in something presentable in some larger universe. And then maybe if I give the category I start with enough axioms and properties, then that presheaf category will have some nice, again, kind of reduce some kind of stratification as of the underrepresentable objects. I have no opinion on how to make this actually work, but this is like something that might be possible. A different argument is, okay, at least for, so there's certain elementary topos that are just interesting. They just appear in nature very often. And so the primary example is in resibility topos. But the example I want to focus in this talk is the filter product. So they're like interesting toposes. They're just not presentable, but people study them for various reasons. And what we could do is like specifically focus and try to prove that these are models of homotype theory, even if they're not presentable. So using some other knowledge, so using more specific knowledge about what these categories are. So that's the goal for this talk. And the general case might follow something. Okay, so before I move on to this filter product business, let me say like a word about elementary topos. As a matter of fact, for this talk, the definition of elementary topos is completely relevant. So if you know what local recursion closed with subobject classifier means, then good. But if not, the only thing you should think of is that elementary topos is like the correct generalization of a Grothendieck 1 topos in some sense. Right? So there's tons of gigantic books written about elementary topos theory and how you can do lots of cool math with it, and then how in the presentable case it exactly reduces down to a Grothendieck 1 topos. So it's like the correct non-presentable version of it, and people have been using it a lot. So that's the only thing you should remember from this, if you don't know already what elementary 1 topos is. Okay. So I want to do like a filter construction, filter product construction. And if I want to do a filter product construction, I should say what filter is. And a filter, there's like a general definition of a filter. I don't want that for this talk. For this talk, filter, I will focus on this particular case. So this is like a restriction, but it's the only case I care about. So what's a filter here? It's just a non-empty subset of some power set closed under intersection and upward close. That's all. And how do we make sense of it intuitively? Intuitively, objects in the filter are like large subsets, right? So this large should be really understood metaphorically, right? It should not necessarily have large cardinality or small cardinality. It's like we're choosing certain subsets and we're designating them as the large ones. And then we're giving them axioms that we expect large subsets to satisfy. Concretely, for example, like if you have two large subsets intersect them, they should be still large. Or if you have a large subset, then something bigger than that should also be large, right? That's what we expect. So this is kind of how we think of them as large. And so in particular, then we can kind of generalize this metaphor here and say if I is in phi, then we can call the complement of I as like small, I guess. Right, the opposite of large is small. There you go. Okay, so I don't know. This is like an intuition if you're not familiar with filters. If you are, then better. Okay, so using this, we can give the definition of a category called the filter product. So what is the filter product? So I start with the category C, and I define a filter product. The objects are kind of obvious. It's just the objects are I index objects in C. So there's nothing really interesting or special about that. But the morphisms are weird, right? So the morphisms are, I choose, so like you should think of it as a tuple. So a morphism is like a choice of J inside phi, like an element, a large subset. And then a choice of maps Fi from Ci to Ci prime for each I and J, right? So you choose a subset, and then for each subset, you choose a map. And now you say, okay, I give it an equivalence relation. And that equivalence relation is given by two such index maps are equal if they agree on a large subset. Okay. In other words, they only differ after a small subset, right? So this is analogous to saying they're only different on the complement of J tree. So it's like almost equal kind of functions. And so there's like a cool fact about them that I think I saw the rest of the reference I found is due to Aleman and Johnstone, which says that if E is an elementary one topos, I is a set, if E is a filter, then the filter product is also an elementary one topos. It's nice. And I should note, they prove something more general, but I will focus on this thing I need. And notice this fails if you replace the word elementary with Grothendieck. So it does not hold. Let me give you an example. Take E to be set, just a category of sets, normal sets, and I be n and phi be the Fréchet filter, which is literally defined as it's in the filter if it's cofinite, i.e. complement is finite. And then in that case, this filter product is non-Grothendieck. So I will come back to this example. So part of the talk will be to talk more about this example. And so notice in this particular case, so remember I said, what did I say? I said J is small, right? If the complement of J is in phi. But what does that mean here? Small here literally means finite. So, right? Cofinite, being cofinite means the complement is finite. So in this case, this literally means finite. So that intuition actually works here very precisely. That being small just means technically finite. Right? And so in other words, then the filter products are maps, collection of maps that differ only on up to a finite subset. So what we want then is to generalize this. The goal is to say this kind of this result here holds also in like this the model category theoretic setting. And here we run into the classic problem is, okay, you need some sort of definition for what correct like analog of a type theoretic model topos should be. And this is the kind of stuff that is still highly disputed among people. So I will just give a definition that gives me the results I want. But I mean, people should interpret it as it's possible to like modify it based on it. So all I want is, I want to take the definition that Shulman gave, so the 4 conditions, and modify them in a way that gives me something workable that I can use in a non-presentable setting. And concretely, what you notice is I have to get rid of this Grothendieck, replace it with elementary. I can keep basically most of 2, except for the combinatorial. Combinatorial has to go. And this is fine, 3 is fine, and 4 is like chaos and madness, right? Like 4 is completely weird, so what do we do here? And so like then the definition that I'm proposing here for this, for the purposes of this, is to just replace the Grothendieck elementary as claimed, kill the combinatorial, keep the rest. Separation localization closed is exactly fine. And here for the last one, so if you recall that one of the implications of these list of stuff that Shulman proposes is that Philip has fiber and confinement univariate universe. So because I cannot prove it anymore, if it's not presentable, I just assume it. Aha. And so here, let me explain what does this last one mean. Has a universe should be interpreted as the category can be filtered in some way, such that this functor fib. So I mean, I guess I should recall. So fib was a functor from the opposite category of E to groupoids, which takes an object X to the vibrations over X, but then the maximal subgroup. So this functor has universe, meaning there's some sort of acyclic trivial vibration, which, so the trivial here is X, so there should not be here. Acyclic vibration, sorry. There's like a typo. So there's an acyclic vibration, where acyclic vibration means in the sense Shulman defines, so not in any other sense. Literally in the sense that Shulman defines in the paper, there's an acyclic vibration from something representable to this fib. So this definition is basically, I would say, as close as it could be to Schumann's definition with like minimal modifications. And so I can give you like more motivation for why this definition is reasonable. So is this the best we can do? Is this the definition should be? I don't know. I'm not particularly dogmatic about it, but it satisfies three conditions that I cared about. First of all, it does generalize Schumann's definition. I mean, by default, almost like every Grothendieck topos is elementary and so on. It still includes all the classical other definitions. So it is a particular logical, type-theoretic, good, but not excellent, which if you know what excellent means in this context, excellent here means it's combinatorial and some stuff, and that cannot hold, obviously. But everything else still holds. So because everything holds, it still interprets Martinov type theory with like a ton of stuff. The things that don't work here immediately are some of the higher inductive types, right? Some of the infinite higher inductive types, they fall away. But like a lot of the more classical types do work still. So you get like a functioning model for type theory with some cool facts. And
can I ask a quick question?
Yes, you can.
Your elementary topos, does it have a natural numbers object?
Well, it does, yes. I claim it does.
Okay.
Well, you have to construct it. I mean, I claim you can construct it by taking the circle type and then pulling it back, and then taking a certain subobject in it.
But you start with an elementary one topos, right? And then put a model structure on that. Did I misunderstand? If you go back one slide.
Yes, that is to here. I'm not assuming as a natural number object, if that is what you're asking. But my claim is you can prove it in this case. Okay, does that answer your question? And so yeah, so 1 and 2 are like, so it's kind of like a sandwich, I guess. It has to be more general than a type theoretic model topos, but it has to be less general but logical type theoretic and good model categories. So, and number 3 has non-trivial examples, which number 3 I haven't like proven or indicated yet, but we'll get there. So that's the claim. Okay. Okay, so I guess this is a good point to. Are there any other questions? Comments?
Can I actually clarify my question a bit further?
Yes, you can.
I was talking about elementary one topos, right?
Yes.
And then you have a model structure on that. And
yes.
Also in Mike's definition, you start with a Grothendieck one topos, and then you have a model structure on that, and so on. Right?
Yeah.
Your definition, you're saying, all right, just put an elementary one. Does that itself have to have a natural numbers object in the classical sense?
Well, a priori it doesn't, but it will have one. That's what I'm.
I suppose what you're saying is that the other assumptions that you're making imply that it does have a natural number object.
Yes.
So you might as well have assumed.
Yes. Yeah.
Yeah. I mean, many topos theorists would say elementary topos includes having a natural number object because most of the time you want to have one, right? I mean, you're not going to start with finite sets, are you? For example, you know, thinking of an elementary topos that doesn't have a natural number object.
No, I mean, I think that's true. I mean, Yeah, I think one of the implications of this stuff is that just by assuming you have having these axioms, you can deduce that you have a natural number object.
Yeah,
That's
I mean,
what I'm
as you
claiming,
said,
right?
sort of coming out of having a circle and things like that, you're going to have.
Yeah, so yeah, obviously there's lots of work. It's not a trivial argument, but the vague argument is you have finite colimits or finite limits, and you have descent. You have like some notion of descent, because yeah, and so then what you can do is you can exactly push out. You can like take the suspension of the points at S0, you get the circle. You can pull it back, and that object should be loops of S1, i.e., the free abelian group on one generator. And then like you prove some stuff about it and then use that you can find some sub-object in it that's a natural number object. It's
right,
a
so
non-trivial
Ali's question, just to clarify, Ali, did you mean like just the first condition or all conditions?
Yeah, so I just meant the first condition, but I guess even if you put something like, I don't know, like finite sets, which doesn't have a natural numbers object, you wouldn't be able to satisfy the other conditions anyway.
Yes.
Yeah.
Number 4 would fail hard.
No, so I think Nima's claim is limited to things that satisfy all 4 axioms, not just the first one. Yeah.
Yes. Yeah. Of course. I
That's
mean,
the
you start
point
with
Andy was making.
Yeah, you need a category which has all 4. So in particular, with an elementary topos, but it has all these other ones. And so finite sets would not work. Yes, definitely not. That would fail really hard. Okay. All right. So any other questions? What? No. So okay. So moving on, the first step towards any search result about filter products and these kind of like model topoi is we need model structures. I mean, at least that's the approach I'm taking. And so this slide, if you just look at it, it's just saying that if I start with a model structure and a filter, I can give the filter product category a model structure again. And I should be clear here, model structure should be understood in a finite limit colimit sense. So in the old school equivalent sense, I guess, and not in a more modern, usually like more modern people, when they mention model categories, they mean like small colimits and limits. Here, I really mean finite colimits. And so basically, if you look at this definition, I mean, it's almost like if you're familiar with ultra products, depending on who you are, it's like if you're familiar with ultra products and Large's theorem, I'm basically reversing Large's theorem and making a definition. I'm saying, okay, my fibrations, cofibrations, weak equivalences are determined to be exactly the ones which are under some filter. Right? So it's like I know what Large's theorem is and I make it into a definition. And if this slide itself, I mean, I don't know, I guess I claim that I proved this, but there's nothing like fundamentally topos theoretic about it. This could have been in any book on model categories. I actually, like, you could just give this to like a really young PhD student or like advanced master student, and they could prove it. Right? But I guess my observation is that this is interesting. Like the intersection of model category theory people and like filter product people has always been empty. So nobody just studied this. Yeah. So there's nothing really like foundational about this, I guess. And the only fun fact about this is really use all 3 conditions of a filter, which are like was like a nice observation. You cannot weaken them, as far as I could tell. You could not just relax the conditions. Okay, so let us observe that some of the properties of a model category that you start with will transfer over to the filter product. And essentially, the standard is, can you depict it as a kind of finite condition? It will transfer, right? So the finite limit and colimit, that's not due to me. That was already known by the Topos theorists, right? So the foundry obvious to find the properties will like finite limits and colimits would transfer, Cartesian closure would transfer. That was known. And because all the fibrations, cofibrations, weak equivalences are defined in terms of the original model structure, any kind of standard property like properness or solutionalness or something, or cofibrations being monomorphisms, right, which is the condition we had, will just transfer over. On the other hand, what will not transfer is any kind of infinite condition, right? So if the category you start with has infinite colimits or limits, or is locally presentable, or if the model structure is cofibrant generated, then there's no guarantee that this still holds on the filter product side. So it might, but there's no guarantee in their counterexamples, as we shall see. And notice this model category definition is compatible in a reasonable way with the infinity categorical definition. So this talk is focused on model category stuff because, well, it's a talk to type theorists. I want to actually give models. So I want to use strict categories. but you can take like a more infinity categorical, quasi-categorical kind of approach towards filter products. And you can prove that this definition of a model category, this is model categorical definition, agrees with taking the filter products of the underlying quasi-category. So it's homotopically correct in some sense, which is good to know. Okay, so I have a definition of a model structure. I know it's reasonable, so I can move on to the main result. Yeah, and that is, if I start with a type-theoretic elementary model topos, in the sense defined before, I said, and a filter, then the filter product on it with the model structure obviously given before is again a type-theoretic elementary model topos. All right, and so this exactly generalizes the result I stated by Adamman and Johnstone. So I guess I have a lot of time, so I can do a lot, but I was not sure. So up from this point on, I want to do an example, and then why we should care, and then something about the proof. So that's like the plan. And depending on how much time I have, which I seem to have a lot, I can actually do all of them. Yes.
Could I ask a question? Yeah.
Yes.
So I'm trying to remember my elementary topos theory, but I think I do remember it. So the filter model construction, if you do it to a topos, that's a special case of having a left exact comonad on the topos and taking the category of coalgebras, and that's an elementary topos, whether you start with a Grothendieck one or an elementary one. And indeed, that's the typical way of presenting the result of a geometric surjective geometric morphism from the original topos. It's always presentable as the coalgebras for a left exact comonad. So there's an obvious question to you: is can your main theorem be generalized if I start with a left exact comonad on my type-theoretic elementary model topos? Is there a similar structure on the category of coalgebras? So that would subsume your main result as an even more general result.
I have not thought about it, so I can't tell you. But this sounds, yeah.
It's definitely worth trying.
Yeah. I mean, you're absolutely right. This is.
But if you start with a Lex comonad on a Grothendieck topos, isn't the result also Grothendieck?
No. It's a way of getting elementary toposes.
Okay.
I believe I might be misremembering, but that's what I have in my head. We'd have to go and look it up, but I think that's right.
Don't Lex comonads correspond to surjective geometric morphisms?
Yeah, that's true, but we're not over any base necessarily, right?
Okay.
Yeah, I could just be, becoming senile.
No, I mean, I'm not familiar with the results, so therefore I cannot, like, obviously the step would involve checking the result and seeing how it compares. I don't know because I haven't checked, but this is a good place to like look. Yeah, so where can I find this? Maybe you should tell me, and then I can like look this up more carefully.
Yeah.
The only thing, so this result, I mean, this the work is kind of motivated by, I did this first in like an infinity setting. I talked about this also like in June or July or something, I feel, at some point. So there's an analogous result where you start with some kind of infinity category. And then do like a filter product there, and then you have some transfer of properties. And I'm a little bit like skeptical about like co-algebraic structures and infinity categorical settings, because like things are always like tricky. But for the specific case of model categories, this might work. I don't know. I have to think about it. That's a good question, definitely. Any other questions? If you have any other suggestions for like cool things to prove? Nope. Okay. Then, so before I do anything else, let's do actually an example. So if you didn't understand anything up until now, maybe you can just repeat that example and take it home. And remember, okay, there's this one example I have in mind. So I want to give the example of like E to be simple sets with the Kahn model structure, which we've known for decades that this is a model for HoTT. take I to be the set n and phi to be the Frechet filter. Again, to remind you, that just means I is in phi if and only if the complement is finite. And then the theorem should deduce that it is a type-theoretic elementary model topos. And the claim is it's not Grothendieck. So let's study this claim a little bit more carefully. And as a matter of fact, I claim that all of these three hold. So the underlying category is not locally presentable, and that means the model category is not combinatorial. It doesn't have infinite colimits, and the natural number object in that category is non-standard. So I want to prove all three. And how can I do that? So first of all, just observe that 2 implies 1, because if you don't have infinite colimits, being presentable, part of it is having infinite colimits. So if you don't have infinite colimits, you're not presentable. And 3 implies 2, because if you do have infinite colimits, then taking the infinite core product indexed by the natural numbers of the final object will be a natural number object and will be very standard. So if you have infinite colimits, then this holds. But there are examples where you still have a standard natural number object, but you still don't have infinite colimits. So, but if I can prove 3, then I'm good. So let's do that. How can I do that? Let's study this category more carefully. So the example is more of an excuse to tell you what the category is. Right. So what are the objects? Objects are paired like tuples like this, right? Indexed by the natural numbers. And morphisms are, well, let's just stick with this. So tuples like this. And then I have to say I can identify morphisms like this. And when do we identify them? And the argument is if they only differ on a finite set. But it's a standard fact that any finite subset of the natural numbers has a maximum element. So this is just equivalent to saying that there exists some natural number such that for anything bigger than that, fn and gn are equal. So this is like a little bit different phrasing, but it's like much easier to think about. So all the eventually equal maps, right? I'm taking chains of spaces and eventually equal chains, each eventually equal classes of maps. Easy. And it's like a reasonably standard observation that the natural number object here is given by just take n at each level. And that's because, I mean, you just start and give it the universal property, just transfers. Like there's nothing fancy about it. And so my claim is that this is a non-standard natural number object. And how can I see that? And maybe you don't know what non-standard means, so this will also explain that as well. So I have inside my natural number object, I have the standard natural numbers, which are given by, well, just level-wise n, let's say. N is some fixed number. And being standard would mean that all these maps together, they're jointly surjective. And my claim is they're not. How can I see that? I take the following natural number. That is, I call delta, and it's 1, 2, 3. So the nth digit maps to n. And if I now pull this back, what happens? They agree exactly on one spot and nowhere else. Oh, no, this is wrong. This is the nth spot. Oh, sorry. No, go away. Well, this is cool. I didn't know it can do that. Ah, okay. And then empty. There you go. And this is just the empty object because it's eventually empty. So it's just empty. So delta is a non-standard natural number. It doesn't intersect with anything. That's kind of weird, right? Like it is completely behaved. It's outside of all of the standard natural numbers that you would get in Khan, let's say. So in particular, then all of the other results follow, right? It doesn't have infinite colimit, it doesn't have infinite coproducts. Like it doesn't have countable coproducts. This already has to fail, let alone all the presentability, cofamily generators, everything else. Why should we care, I guess? This is a good point to say, okay, well, why does this example matter anyway? And so I should be honest and say this technique for constructing new models doesn't generalize in a way to other kind of interesting examples, as far as I know. Like it proves filter products, it could prove other like things similar to that, but it won't generalize to some arbitrary other examples. So I guess one place where I'm hoping that this could be interesting and useful is basically just more standard topology. In the sense that I guess this audience is not a good audience because I mean you're in a talk where the first 4 letters of the title of the talk is hot, so you're already probably interested in type theory. But if you like find like a homotopy theorist on the street and ask them why should we care about type theory, then very often there is not a good answer to it, because if all models of type theory are presented like Grothendieck toposes, then they just use some fancy like just presentable techniques to just prove everything. But if you have non-presentable examples and can start proving stuff about them, that's the kind of place where really like results about HoTT become valuable, right? So the fact that I know that an example like this, regardless of how weird it looks, is still a model for HoTT, has kind of nice implications. It allows me to like deduce certain things about it. So I can start talking about like homotopy groups of spheres in this model, right? For example, one thing we know is so HoTT people construct truncations, but their truncations are indexed by the internal natural number object. So the fact that if you, for example, have here an non-standard natural number would mean that we have extra truncations that are not externally visible. They just literally exist internal to the category, but they don't exist on an external level. So yeah, so one place to take this, I hope, is to observe that you can use HoTT to do cool iterative topology and convince the unbelievers. You're already believers, so I don't have to convince you. Okay. So the last part then is say something about the proof of the main theorem. And so what does the proof imply? What does the proof need? We need to prove these 4 statements, right? We need to prove that the filter product has the 4 conditions stated in the definition of a type-theoretic elementary monotopos. Condition 1 is exactly the result by Shulman and Johnstone, so that's good. And condition 2 follows from that long chart, right? Like everything I said is already just kind of like a finitary property of the topo or the category. So that's good. Condition 3 is also like just local condition close. Condition is fine. So the main sticking point is number 4, right? So what can we say? How can we deduce that if E has some kind of universe for a certain vibration functor, can we deduce that the filter product also has a universe? And so here, let me see if I can make like a short, vague argument. And so the claim is, if U is a universe in E, then just U, just like the constant U indexed by I is also a universe. But now inside the filter product. And if I can prove that, then I'm good, right? This covers everything. And so here I'm going to like, so the goal is to show, what is the goal? The goal is to show that so if I have a diagram like this, so these are indexed by I. So there should be, yes. So these are like representable functors, represented by, so this is just represented by U, and these are just represented by maps AI to BI, char co-vibrations. And here I have my fib functor. And the goal is to observe that this has a lift. So this is what it means to be an acyclic fibration in the Shulman sense. That's what I need to prove, right? And what we can do is, well, we observe that you can kind of just compute the diagram. So I can just make this into a product of these various AIs with some equivalence relation. This is also just a product of various representable functors. Again, with some equivalence relation. And this is the same. But then fit is not, right? So what is happening here? Let me come back here. So this functor has values fib of x is fibrations of fib phi. I guess it should be an xi. Has fibrations over xi. But then the problem is, if you recall, a fibration over xi is only something that is a fibration from some point on, like a fibration like in the filter. So it's not necessarily fibration everywhere. So this fib is actually not just a product of the fib functors. But here's what I claim is that you can kind of build some kind of equivalence to just a functor that is fib level wise. So the key claim of the whole thing is that there is an equivalence like this. There's an equivalence of group weights. And the argument involves kind of finding appropriate objects in certain equivalence classes. And so then, well, what I need to do then is show that this diagram has a lift. And showing that this diagram has a lift follows from the fact that U is a universe inside the original category. So this will have a lift. Yeah, so there's like a nice cheat you can take here. Like the result really just follows by like, okay, knowing it for the original category and just like then showing it trace, it goes through to this like this setting. Okay, with that, I'm done. So let me know if you have questions.
Okay, so before we do that, let's thank Nima for this great talk. So we're going to do silent applause. So yeah, please join me in thanking. All right, and now we're going to open the floor to discussion. If anyone would like to issue any updates on the topics discussed before as well.
Yeah, so there's some stuff on the chat, it seems, about. Okay, I see.
I know, so if anyone would like to say anything about the things that were
yeah, so okay, I see. So Andrew says it seems that Jonas was correct. Okay, so it's really then, so if you start with a Grothendieck topos, you will get a Grothendieck topos using this. I see. So this wouldn't actually help in this. Okay, it still would be okay, I guess. Okay, if it's really just, I guess even if you knew that if you start with something elementary, you get something elementary, you could apply it to something that you already know is elementary, like this one, and then get more elementary models. So that would also still be interesting, right? But I will have to look into it. Like I can't just comment. For Samuel's question, I have no answer. What is the precise relation between algebras over Lex comonads and elementary one toposes? Maybe somebody else has an answer for this. I have no idea.
No, it's okay. I've had a private answer to that, which apparently is that it's like yeah, they just classify or induce geometric surjections between toposes. That's the answer apparently.
Okay, that makes sense. And yeah, so Egbert, like the good comment. Thank you. Yes, like I kind of mentioned that already, right? When I mentioned like homotopy groups, right? So implicitly in saying that there are more homotopy groups, it's like exactly there are more spheres, right? So in particular, one cool thing is, so I focus on the Fréchet filter here, right? But what you do is expand the Fréchet filter to some ultra filter. And then what you would expect to happen is that you get a topos, which is generated by the final object. Because that's already true in the elementary, like in the more classical setting, not classical, in the one setting. So you should get some kind of model of spaces generated by the final object, but with additional natural numbers. which because you have a non-natural number object. So you get some sort of spaces, but with more spheres and more homotopy. So what happens there? I don't know what happens, but I think it's worth looking into.
Okay. Anyone else? Questions, comments? Updates from Nevada?
Do we have any updates?
I don't even know what's going on in Nevada. Okay, so maybe I'll ask a question then. So you mentioned the thing about switching between injective and projective model structures early on, right? And the result that
that's the result of
right when you talk about presentability and Mike's result. So right. So I guess the question is like, why would there be an issue if you just like wanted to stick to one? So I kind of see that you would be needing injective at some point, right?
So I know that you need injective to make the HoTT work, right? That's like, so when Shulman does this, he uses injective to make type theory work.
Yeah, so that I get. Projective.
I mean, I don't think you need it. Just a more natural thing to do from a homotopy perspective, right? Like, I mean, you start with the Kahn model structure, and then what do you want your fiber objects to be? Just what do you want your fibrations to be? Just the one that are just level-wise Kahn. So just it's like it's the more intuitive thing. If you know nothing about type theory but know a lot of homotopy theory, what would you do? Like, what's more reasonable to you? Just go and project that. And so that's
right. But like, I mean, but my question is like, okay, so this, like, I grant that point, but my question is like, you know, like, why say, okay, maybe it seems more like unnatural at first, but at least like then I can be consistent and just use one model structure, because like ultimately when you want to interpret things between type theories and infinity categories, right? Like the way I would think about it is like I want to have as direct comparison as possible, rather than go through and then coherence and then this, right? So this injective projective swap seems to essentially what it seems to do is it just it inserts somehow the identity functor in the wrong direction.
Yeah, I know. Yeah, I mean, I agree. I mean, it's like, I guess you just have to change the convention, right? I mean, yeah, I agree with that, but this is like in hindsight. And so hindsight was 2020, as I say, right? And we are in the year 2020, so it's chaos. No, I think, yeah, so I guess you could just go back and define presentable model categories, like these like universal homotopy theory stuff, and then model topos and all of this using injective model structures, and then improve everything. But yeah, like people for some reason they started with projective, and so just stuck. But yeah, I'm pretty sure you could probably switch everything just over to injective and have still like the model category side, and then move on from there. I was trying to stick with the history, right? So if you like look at Charles' notes or something on the model topo stuff, he uses, but that's just what historical people did, right? So I don't think there's any foundational. Maybe I'm wrong. I don't think there's any foundational reason. I want to say it's just the convention people picked and just went with it. But because really, in the end, what you need is you just need some kind of profile-engineered model category that works well and does the stuff you want. Both of them do for Kahn complexes. I would say you don't need to. You just have to change the culture on
it. Okay. Anything else?
So if we have these non-standard natural numbers, is there any way to see that within HoTT? Or is that something we can only see on the outside of it?
I'm not sure how to interpret that.
So I mean,
how do we see it within HoTT?
Is there some sort of like axiom we can add to HoTT in order to say, yeah, we have a non-standard natural number? Or does that make any sense? Or is it something that only exists in the model?
Maybe I feel like the actual hot people might be more qualified to answer that. But like, I mean, so you're saying that you cannot make sense of this pullback square like in hot or something? Like I'm pretty sure you can define the standard natural numbers, right? I mean, it's literally in the definition of an NNO, right? I mean, there should be like the standard natural numbers. So now the question is, can you not just, is it like, so you're saying being non-standard would mean there's an additional map from the final object. So it pulls back always to something true to the initial object. My naive guess would be just make sense of this exact same argument.
Well, the problem is that that argument's using the external natural numbers. You're saying something's true for each little n, which is an external natural number. So I think the question is there some statement you can write down purely internally, which would hold in your model, but which wouldn't hold in all models?
No, I mean, you can make sense of the standard natural numbers internally to any elementary topos, I want to say. I mean, yes, I use it here because I mean, that's the example I'm giving, but that doesn't have to be true. I mean, you have a distinguished zero element, right? And so one is then just S of 0 and so on. And so is there like a map from the final object that is not covered by Sn of like the successors of the 0 element?
But you can't state that internally. You can't quantify over just the successors of 0 internally.
Well, the smallest object that contains 0 and is closed under successor will contain all non-standard natural numbers also. That's the confusing thing. So
no, I agree. I completely agree with that. I'm saying
really difficult to. I appreciate also. I thought about this. It's really confusing.
No, I completely agree with that statement. I don't like. Yeah, I find it confusing too. It's weird. But I agree with. I'm saying. Oh, I see. Yeah. Okay, I see. Yeah. You cannot say for all n. Yeah, I guess maybe you need some kind of extra. So yeah, if I want to say I have like 1 and then n, and then I have like Sn here, and so I want to say now for all n this with some other like some other d or something. I want to be So if I want it to be for all n, then yes, maybe that's an issue. Interesting. Yeah, I never thought about it this way. So maybe not.
If I may say something more on non-standard natural numbers. So even if you take set or spaces to the n, the countable product of spaces, then I can take a global section of the natural numbers object, which has a different value at each index. And one might already call this non-standard. So I was always confused about what makes the non-standards in the filter quotient special as opposed to that.
Is it? I didn't claim any specialty. I don't know. Wait, what is your example? I mean I didn't. Is it not? I mean, so the sense of non-standard I mean is that it's like not like so the maps from the so-called the one from the successors are not jointly surjective. So that's for me the non-standard natural number object. Does that hold in the example you just mentioned, or?
What I'm saying is that you take sheaves on a countable space, and then you could take a discrete countable space, and then you take a section that is different at every point. And I mean, the natural numbers object in sheaves on a discrete space is just constant everywhere. But then you take a section that is different everywhere. So it's basically, I think you're using this function probably. And it's also different from everything that is obtained by externally iterating the successor on the 0 section.
I mean, it is different, but it's not. You can write it as some kind of. I would assume. I mean, I have to think in my head, but I feel what you are explaining can be written as a co-limit of those of the restrictions of the standard natural numbers. If I understand the example correctly. Maybe not. I mean, maybe we should explain this better. But
I don't really have a question. I just want to say that for me, the concept of non-standard number is confusing.
Yeah, I mean, okay, I took the notion of non-standard here in this sense from the elephant. So I should say this is not due to me. This is like this definition of non-standard is in the elephant.
Okay, that might be a good place to look.
And I could try to find the page. I have to look it up. I have not memorized it, but I know like this phrasing of non-standard as the successors are covered. That's in the elephant, and this doesn't satisfy that. Right, so literally it doesn't intersect at all in a non-trivial way with all of the standard natural numbers at once.
Okay. I see, thank you.
I think there's something I don't understand, like, because from what I understand, what we prove in HoTT should be true in every model. So how could there be a way to see those non-standard natural numbers within HoTT, because some models don't have them? So how can it be possible that we see them, or we can prove properties about them in HoTT?
I think the question is there a statement you can write down in HoTT that holds in this model, even though it won't hold in every model? Can you somehow see that this model has some different properties?
Similar to like the axiom of choice.
Exactly. Yeah, the axiom of choice holds in some models, not in others. So it can be expressed internally in HoTT as a statement that changes and
Okay, but it won't be something we'll be able to prove, though. It's just something we can state, right?
Mm-hmm.
Okay, I see.
Yeah, I mean, if you could prove it, then it would hurt everything, right? That would be it.
Right? We have more time, so any other questions or comments?
Maybe people are waiting for you to turn off the recording so they can ask like the secret questions or something.
Well, so before we do that, let me make a final call for questions and comments, and then we can turn off the recording and ask all the embarrassing ones. Okay, well, before we turn off the recording, let's thank Nima again for this great talk. And that's it. We'll see you in 2 weeks.